Good. And the clicker works too, I assume. Good. Okay. So I actually would like you to think about these graph limits a little different from how Jennifer was thinking about it. So instead of using these subgraph counts or the free energies of statistics models or a cut distance, I really want to think you as sampling of a basis of graph limits. Okay, so you want to, even if you're not interested in a limit, if there's a huge graph, maybe it's too big for you to actually see. And what should be important about it should be something you can see when you sample a small piece of it. And so I would want you to think that if you do sort of a more conceptual limit, that it should be therefore based on some kind of sampling. So this picture will be very familiar to Peter. There's a long history. I will go into the history in a moment. But so imagine you have some large combinatorial structure which is out there somewhere in the cloud. You don't see it. And you want to know what is sort of the limit. And imagine you have some sampling procedure which allows you to get a small, let's say, subgraph, right? So if this huge hidden graph of social connections, and then your local Facebook group gives you sort of some local sample of that graph. And now, for all practical purposes, if I'm a statistician and observe this sequence, if the distribution of the small objects doesn't change anymore, I would call these objects convergent. Okay? So we define the sequence convergence if the small objects converge in distribution. And then what is the limit? Well, the limit is just a distribution over these small objects. And it turns out that if we have enough symmetries, then you have actually a compact representation. For example, if the symmetry is permutation of the vertices, then you get the Aldous-Hoover theorem and you get a graphon. Okay, so this is sort of the picture I want you to keep in mind. And now I want to sort of go to the sparse convergence we were talking about. Okay, so before doing that, let me do some review, which I can probably do fast because my guess is Tamara has done all of that yesterday. So left convergence, how can we understand that? Well, Jennifer already talked about it. You choose sort of some random vertices, x1, xn, in your vertex set, IID uniformly at random, and then you get a random induced subgraph. Okay, so that is your small object you output. Okay, and it has vertex set k, and you get an edge whenever there was an edge in the original graph. And now we call a sequence of dense graph left convergent if this distribution converges for all k. And it's very easy that you can sort of do inclusion-exclusion to get all the subgraph frequencies from it. So it's actually equivalent to the notion Jennifer mentioned. But I don't want to think of it as subgraphs. I really want to think of it as these random objects. Okay. Now, with that, what is the limit? Well, in the simplest case, you could just say, well, it's a collection of probability distributions for all k's, right? Not very satisfactory. It turns out that in this situation, the collection is projective. If you delete a vertex, that's the same as sampling k-1 vertices. So that means you can, so if you have that, we consistently build them up by Kolmogorov's theorem or whatever to an infinite random graph. Or formulated differently, you have an infinite random array which is symmetric. Okay? And now this array has a few properties. It's exchangeable because you chose x1 up to xn uniformly at random, while that's the same as choosing x pi of 1 up to pi of n uniformly at random. If this is permutation, you just change the labels. And it's extremal. This array, sort of what you sample here and here, is independent, and then you can show that it must be extremal. Yeah, maybe. So it's extremal in the set of these probability distributions. Okay, so the limit of a left convergent sequence of dense graph is an extremal exchangeable array. Okay, and now we use Aldous-Hoover. So Aldous-Hoover is the analog of the Definetti theorem for 0, 1 valued infinite matrices, and says the following: if you have a symmetric extremal exchangeable array, then there exists some function w which is symmetric, such that we can generate the array by first choosing the features x1, x2, and so on, IID in 0, 1, and then choosing again independently of what we have done before, the connections just with probability w of xi, xj. Okay, so this is Aldous-Hoover, which then tells you that actually this is a compact representation, that I can represent it as a graphon. Okay, now the notion of left convergence, originally we didn't do any of that. We did the subgraph counts. We were sort of blissfully unaware of that somewhat. We knew that Aldous is a name, and I don't know even whether we knew the name Hoover, and we certainly didn't know the Aldous-Hoover theorem, even though we probably should have, but we didn't. And neither did Lowas-Szigeti when they proved the existence of the limiting graphon. But actually, once we introduced this notion of left convergence, we could have used the Aldous-Hoover theorem. I gave you the proof here in a few lines of the existing of a limiting graphon. And that was actually first pointed out by Diaconis and Janssen, and independent by Tim Austin, who pointed out to us, well, the whole theory is very nice, but the limiting graphon is sort of trivial. That's just Aldous-Hoover. Now, this very explicit formulation in terms of sampling, we sort of formulated like that in our paper with Victor and Henry Cohn.
Victor is on the market.
Yes, Victor is
very good. He's on the market.
Yeah, he is a postdoc, partially supervised by Peter, and he's looking for a professorship. So now how do we want to do this for sparse graphs? Okay, so if you do the same thing as before, you have a little problem, because what is the expected number of edges in this induced subgraphs? Well, there possibly k choose too many edges, but there is this density, so actually it's only rho of g times k choose 2. And if now the density goes to 0, then for each fixed k that goes to 0, so with probability 1, the limit is the empty graph. So that's not very interesting. I mean, it still exists, but... So how can we get around that? Well, the way to get around this is you define a sampling procedure where actually you continue. So you don't just sample a fixed number k, but you sample more until you finally see something, okay? So it turns out that, so we will want this k times k minus 1 to grow in expectation like 1 over rho of g, because then, which one is this? Because then this cancels this thing out, right? So this is just, so what do we do? Well, we take k to be a Poisson. I really don't see where this thing is there. So we take it a Poisson random variable, or you can think of it, it's a Poisson process with density k on the vertex set, and then you output the sample graph after deleting isolated vertices. And then if you take this kappa correctly, such that this rho and everything cancels out, namely you choose a t over, so some constant over square root of number of edges, then actually you get uniformly in rho of g, t squared over 2 edges. Okay? So that at least makes some sense. And now we define a sequence sampling convergence if these small sampled graphs converge. Okay, and you had to delete all the isolated vertices because you'll find tons of them. So now this is sort of not a super difficult theorem because it's essentially compactness. So any sequence of graphs will have a convergent subsequence because, well, I mean, you have sort of these distributions on countable graphs, and that is a compact set, and so you must have convergent subsequences. But what is the limit? Okay, this is sort of the difficult and interesting question here. And so let's just do what we did before, okay? So a priori, it's just now a process of unlabeled graphs. For each t, you get one, so you get a random process instead of a random sequence. And so that raises the question, is there some analog of Aldous-Hoover, which you could apply to this sequence? And the answer is yes. And instead of exchangeable arrays, you will have to talk about exchangeable random measures. So I will get to what that is in a little while. But let's go back understanding this process a little bit better before. Okay? So we said it's a sequence of graphs. I claim we can also transform that into some random measure on the quadrant. So how would I do that? Well, we have this random graphs here, which were obtained by having a Poisson process of a certain density on the vertex set. And the density grows with t. So now instead, I do a Poisson process on the set R+. Think of that as the time axis times this. And now if I forget all Poisson points whose first coordinate is smaller or equal, now if I keep those whose first coordinate is smaller or equal than t, then the induced Poisson process on the vertex set is just one with density alpha, right? With density t times whatever we had, right? So that is sort of gives you exactly the right coupling here. So now we have sort of coupled this process, and now each vertex has two coordinates. One is xi, which you think of the feature, and the other is the time ti where they're born. And now what we do, we just use the times at which they are born to put little random point measures in the quadrant. Okay, so if I was born at time pi and, I don't know, square root of e, then you put a point in the plane at pi and square root of e, and so on. So you look at all the edges, and you always sort of, whenever there's a connection, you put a point in the quadrant. And since t goes over the whole real line, this is now a random measure over the positive quadrant. Okay? And this measure has sort of nice properties. So first of all, let's sort of define the limit. So again, this set of measures, you can put a nice topology on it because, well, the underlying cis is R2 on which you have a nice measure, and then you can have the Borel sets on it, and all of it sort of carries over, and eventually you can metricize this set of random measures, and then you can look at this limit. Maybe you have to look at the subsequential limit, and which now is a little bit more work. You then have to prove that actually if you're sampling convergence, that this is equivalent to these processes, these random measures converging as random measures. Okay, so that is actually part of the technical stuff you have to do here. What are the properties? Well, one nice thing, this is now, again, exchangeable. Now, what does it mean for a random measure to be exchangeable? Well, you could actually just talk about permutation. So you could just take sort of dyadic intervals and just permute the intervals around and ask that this is true for all, sort of no matter how fine it is. That's one version. Another version is you ask that the distribution is invariant under joint measure-preserving transformations on the two axes. It turns out that they're equivalent. Obviously, this permutation is one possible measure-preserving transformation, and since you make it finer and finer, you can approximate all of them. It's not an easy theorem that the two are equivalent, but Kallenberg, in a book of 180 pages, proved it for you. Or maybe it's 300 pages or whatever. And why is that true here? Well, we chose a Poisson process on R plus cross V of Gn, and if you apply a measure transformation, preserving transformation on this R plus, you again get the same density of Poisson process because the Lebesgue measure here is invariant under the measure preserving transformations by definition. So what you get as a consequence is that your random measure is invariant in distribution under this joint measure-preserving transformation. Or think of them as just the same permutation on the x-axis and the y-axis. Okay? And second, this thing is again an extreme point in the simplex of exchangeable random measures. Okay? So again, if I have two random measures, well, if you add one and another, if I choose one with probability a third and one with probability 2/3, it's again a random measure. And if it's exchangeable, you can easily see that it stays exchangeable. So it's a convex set, and then you can again use a general theory of sort of showcase simplices or whatever to talk about sort of what are the extremal points. And again, very similar to the reason why these independent pieces of the infinite matrix in Aldous Hoover were independent, you get something like that here, and then you can show that the measure has to be extreme. Okay, if it were not extreme, then it couldn't be independent. So that is the case here. And now we just need an analog of Aldous Hoover. And luckily, that actually exists. Okay, Kallenberg proved a theorem for general exchangeable random measures. Ours is a little specific because it's counting measures. I have sort of at each point I have sort of a counting measure, and actually a very simple counting measure, namely a simple counting measure. I either have 1 or 0s there, right? I have all these delta functions. So if you, and finally it's symmetric. So so the Kallenberg theorem doesn't only give you a graphon, so it gives you what Jennifer showed you. So in particular, it gives you that you have a Poisson process and you have a function W and you connect xi and xj according to that, but it has 6 additional terms, if I remember correctly, which luckily a lot of them here you can rule out because we know, for example, you could be exchangeable by just having Lebesgue measure. So uniform Lebesgue measure on R plus squared would be exchangeable, right? But if I have counting measures, that can't appear. And so there are many pieces like that in the Kallenberg theorem you can rule out. And once you do that, you end up with what's called a Graphexes. Okay, so this was first observed by Roy and Weicht, so by Victor and his advisor Dan. They didn't think of sampling convergence. They actually didn't think about convergence at all. They just were trying to generalize Caron Fox, who also knew about the Kallenberg theorem. So I will go again through the history in a moment. But so they defined the following object. They didn't do it as general, but let me define it in the most general setting. So you have some sigma finite measure space. By the way, nobody defined for you what that is. So a measure space is sigma finite if I can cut into countedly many pieces which are finite. Okay, and a finite measure space is just a probability space multiplied by some real number, right? So if the total mass of the measure space is finite and I take a countable union of those, that's a sigma finite space. And so you can do that in general. So you have a feature space which is sigma finite. Think of RD, for example. And then you have some sigma algebra, how fine you want to make your observations. You have some measure. And now you take a triple. Okay, so we have a graphon as before. It's an integrable function on the feature space squared. You have a second function, which is called the star function, for we'll explain in a moment why. And finally, you have a constant, which is called a dusty density. And for reasons which will become clear in a moment, you define a norm on it like this. Okay? And now you create a process very similar to the one which Jennifer discussed. Okay? So you have your Poisson process with increasing intensity, so at intensity T times mu. Okay, so more and more and more points. You join 2 points with probability W. But in addition, at each point, you add a star of degree Poisson T times this function. Okay, So maybe W is 0, you just throw down all these Poisson points, and then depending on your feature, you have sort of a lot of children, very few children, and otherwise you're isolated from the rest of the world. Okay? Or maybe even that part is 0, and you just have this part I, where is it? Here, the dust intensity. So we just add isolated edges at rate t squared times I. Okay, so you have all these lonely couples, they never have children, there are no stars, nobody has friends, just sort of the lonely couples living in this world. Okay, so, but it turns out that if you put the 3 of them together, you get the most general, and now you again label sort of the points by their birth time, and then you get a random measure, and that way you get the most general random measure. And that's Kallenberg's theorem, except that Kallenberg, well, he didn't have symmetric, so the W can be different. He didn't have that the measure has to have their value 0, 1. So instead of being just a function 0, 1, it is a random variable. And in a similar way, this guy you could have sort of stars where each of the edges going out can be multi-edges, and this can be multiple. And then there are other parts which sort of are not appearing here because you can have a mixture of having something like that along one axis and Lebesgue on the other, or just Lebesgue. There are all kinds of complicated terms. So he has sort of 8 or 9 terms, but these 3 survive if you assume that you have a simple counting measure. Okay, so, and now, so this is sort of a theorem which results from this observation. A theorem is sort of a little bit more complicated, but I think I gave you the heuristics. And it relies on this 400-page book by Kallenberg, which in addition has some errors. Some errors in it we had to correct because it actually turned out to that sort of it produced a little contradiction.
Kallenberg said it can't possibly be wrong because everyone's been using it for 20 years. So we gave him a counter.
Well, first I wrote him a note and said, look, here in this proof you make an assumption you're not allowed to make. You haven't proved it. He said, no, it doesn't. I said, fine, you know what, this is boring. I just do the old-fashioned way. Here's a counterexample. And then he said, well, I guess how do you fix it? Anyhow, it's in the end. Yeah, one of our young co-authors really. So, okay, so you use this Kallenberg theorem for random measures, and more or less the rest is a lot of work, but it actually turns out to. I mean, the main point was really to come up with this notion of sampling convergence. So some historical remarks. So in order to model sparse random graphs, Kallenberg's theorem was first used by Caron and Fox. So she was the first, and the two of them were the first one to observe that if you use exchangeability on this continuous random variable instead of vertices, that it allows you to regenerate a model which is sparse. In their example, the graphon, they only had a graphon, they didn't have a star function or an intensity, and their graphon was the simplest possible you could think of, was a rank 1 function. Okay.
So f of x times g.
Then Victor and Dan introduced the notion of the graphex. So these two guys realized you can use it, but they didn't quite know how to use this complicated theorem to come up with the most general possible model. That is due to Dan and Victor. They sort of said, okay, if we want this most general exchangeable model, you get a graphex. And in general, actually, this graphex might not be integrable. But it turns out, and then we wanted to relate this to notions of graph convergence. So we came up with this notion of sampling convergence and showed that you will always converge to a graphex, and that happens to be integrable in that it says actually this norm smaller or equal than 1. And that comes sort of very similar, very similar to if you look at these empirical graphons in the LP theorem with U-phase, they have norm 1, so the limit will have norm 1. And very similar, the way things are set up here, this norm of W has something to do with the expected edge density, and you start with normalizing in such a way that it's t squared, and the norm of W is the limiting edge density divided by t squared. And it's 1 if you lose nothing, and it's small or equal 1 if some mass disappears to infinity. Yeah?
So you mentioned that some of the Graphon approaches, you can prove the Aldous Hoover types of things with the Friese-Cannon style regularity lemmas. So for Graphexes, are there any connections to sparse regularity lemmas?
There are. So we together with Jennifer managed it with sort of Lazzi Jr., so who was here for a while. So I think, oh, he's still here. Oh, he came back here. We developed a notion of cut metric for Graphexes, and then we proved the Semeredi regularity lemma for that cut metric. And it's a complicated story because with the sigma finite spaces, there are all kinds of masses which can appear to infinity, so you have to introduce something like, just like if you want to compare probability measures, you have sort of the norm of weak convergence. You have similar things here where you have to cut out small pieces of the space to regularize and so on. So it's actually in the end a 110-page paper. But the answer is yes, there is a weak regularity lemma. But the weak regularity lemma may be not as useful as you might want it. For our purposes, the weak regularity lemma is sort of applies to certain sequences of sparse graph which have certain regularity properties. And then you have to work how to deal with general sequences to cut off the pieces which don't matter in the limit, and then use the regularity lemma for the piece you want to control, and then paste the rest back together. And you probably would want just a regularity lemma which works and you can always use for any sparse graph. And I don't think that's what we give you. But it definitely is a generalization of the regularity lemma. I have 15 minutes, while this is nice. Okay, so, and we introduced this thing here. So, what is this resulting structure? Well, I already talked about it a little bit, right? I have sort of these vertices. If I ever make a connection, okay, then, so I have feature xi. If I make a connection, there must be a set of non-zero measure of y such that w of xi and y is non-zero, right? Because otherwise I would never connect to anybody. But if there is a set of non-zero measure, then as t goes on, you get more and more Poisson points in that set. So my degree will go to infinity as t goes to infinity. And so you get this dense core of vertices which are all connected to each other, and they're roughly t many of them because the density of the Poisson scales up by t, and they have roughly degree t squared. Okay, so, and then you get t squared edges in this thing. Okay, it's not really dense because these degrees have a long tail, and sort of this part by itself already can make for sparse graphs, but it's sort of morally it's dense. Okay. Then you have these stars where now you can get a lot of extra vertices which makes your graph much sparser, right? Because viewed from here I have degree 1. So, and these isolated edges, they have definitely degree 1, both ends. So these guys make your graph much sparser. And it has this funny structure that if you look at this limit, everybody has either degree infinity or degree 1. So you have this, so how come we get this funny structure, right? So, well, one thing you could say, it's Aldous Hoover, but can we understand it from the sampling point of view? So let me try to develop this picture for you, okay? So we have this graph which we obtained by taking the graph and then essentially has m edges, and we keep vertices with probability p. Well, we have a Poisson process with intensity p, but p is tiny, so for all practical purpose you just have, you keep the vertex or not. And now let's decompose our vertex set into 3 pieces. A core of vertices order square root number of edges, a low degree part with the degrees much smaller, and a high degree part with degrees much larger. And now we do our Poisson process, so we get random subsets. Some of points might be doubled, don't worry about that, of all 3. And now, what happens now? Well, first of all, this set contains, since the degrees are larger than square root of m, and you only have m edges, there cannot be square root of n many of those. There can only be little o of them. And if I sample with 1 over square root of m, they will disappear. Okay? So these high degree vertices, they just disappear in the sampling limit. If the core does not contain enough vertices, this part will disappear as well. But if it contains enough vertices, then there will be some of them left. It will contain p times order of this many vertices. The p is 1 over square root of m, so this is order of t. And the expected degree of these guys are also order of t. Okay, so that is sort of makes a lot of sense. What happens to the low degree part? Well, I will not give you the calculation, but you can calculate, if you calculate the degree of one of the low degree vertices after sampling, there is sort of the probability that I have degree at least 2, well, I have at least 2 neighbors, so that gives me d squared many possibilities. And I have to survive, and both of my neighbors have to survive. So this is the number of vertices which degree 2 or larger at most. And then this is actually, can be seen if you calculate what this gives, is little o of 1. Okay? So what happens is this sampling procedure somehow is just tuned in such a way that it keeps your core sort of relatively densely connected, but the vertice in the low degree part will in the end only have degree 1, if they survive at all. And now the connections can either be between 2 parts in the core, then there will be this, that will give you the graphon, or you have a piece in the core which connects to many of these low degree vertices, that will give you the stars, or the low degree vertices can connect to each other, that will give you the isolated edges. So this gives you sort of a more pictorial understanding of the Aldous-Hoover theorem, which otherwise is sort of very mystical why it has this strange structure. Okay? And now I will spend a few minutes to talk about the configuration model, because that you will rediscover the Caron-Fox model if we look at sampling convergence for that. So what's the configuration model? I give you just a degree sequence, anything. Okay, so Peter dreams one up, and we put this degree sequence down. Okay, and now we put half edges there, and we randomly match them. And we don't ask that it's a simple graph, so it will become some multigraph, but then it's easy to understand. Okay, so what happens there? Well, let's look at 2 sets. Don't worry about this. This sort of requires a proof and technical. But what happens is essentially you have each of these has sort of, when we sample, we have very low probability of connecting, but we have a lot of possibilities of connecting. And then the law of large numbers is Poisson. Okay, and then you can actually, under this assumption, you can control the distance of the distribution and stuff. So, but this makes a lot of sense, right? You connect with sort of, you have this, right? If I want to connect, so I'm a half edge, the ln half edges around. What's the probability I choose u as a half edge? It's 1 over ln. And so each one in there has sort of, tends to have this degree, and then the number of edges between the 2 sets is this. And it's just the world is nice and God is friendly, and you get the theorem you think should be true. And so now, so that's the number of vertices between I and j in this model is just a Poisson di dj over ln. As long as these degrees are not too high degree, but we already said the high degree vertices, there are so few, if we sample, they will disappear. We don't have to worry about them. Okay? So now if we want to control sampling convergence, what we have to understand is what is the degree distribution after sampling, right? We not want to just, so But it's not astonishing that if we want to understand the degree distribution after sampling with some intensity, that we might want to formulate some measure involving these degrees to characterize it. So that's what we're going to do. Okay, we need some assumption. You can't have that 5 vertices make up all the edges. And now you define a rescaled density. Okay, so you put little delta functions where the degrees are. You rescale them by this object, which is related to the fact we will eventually sample, which with square root of n, L. And if you put this in here, it has some nice property. If you calculate the first moment of this thing, then it's actually equal to 1. Because the first moment will then essentially be sum of di's. And now all your square roots are in such a way that the sum of di's is ln, and there's 1 of square root here, and there is 1 here, and you get 1. Okay, so this is a nice distribution with a finite first moment. And now life is actually nice. Forget for a moment this one. Okay, it took us a while to realize. We first tried to prove this. We said, okay, now things will be obvious. If this distribution converges vaguely, then the thing will have a limit. What does vague convergent means? Vague convergent means it's convergent if integrated against a function with compact support. So function which has support from some epsilon to some large m. Given that this guy has and bounded. Given that this guy has a first moment, we know it decays at infinity. So actually I could just say with support epsilon to infinity, because infinity is no problem here. But it's important to say with support epsilon. And that will now explain to you why this funny A appears there. Okay? So vague convergence gives no information on the degree distribution of low degrees, because that would be delta functions at 0, and my measure is not even defined there. It's defined on the open interval. Okay? So this measure rho in the limit has just no mass at 0. That's just by definition of vague convergence. So now if we look at this object, okay, vague convergence means functions which start at some epsilon. Okay, if I integrate this from epsilon to infinity, here from epsilon to infinity, then vague convergent means it goes to 0. So in other words, this thing, if I restrict the integral going from 0 up to epsilon, it's the same. Now if I integrate from 0 to epsilon, the minimum disappears, so I just get an x. And as I said before, if I then send epsilon to 0, this guy doesn't know what's going on at 0, that will be 0 as well. So what is left is actually this A is just this object. And now you rewrite it, okay, and if you insert it, you get 1 over ln. This sum, if I didn't have this, this would be 1. So this is just the fraction of half edges which have degree little o of square root of ln. So this is exactly the object which I said should be responsible for the dust and the stars. And sort of you need to control that as well, because if that fluctuates widely, then for even n you could have tons of stars, for odd n's you have none, and so on. So you need this guy to converge. But if you have both, you get convergence. And then we can read off the limit, and the limit is as follows. Okay, so you get a multigraph process, because we started with a multigraph. The multigraph process you have, so you now have a Poisson process of intensity t times rho on R plus, where rho is the limit, the vague limit of this measure. And you join I and j with Poisson yi, yj. Remember that the number of edges between vertex I and j was Poisson di times dj over ln. And then in addition, you have loops, which are a Poisson process. You get stars which involve this quantity A, and you get isolated edges which involve A squared. So this will be these things connecting low degree vertices to low degree vertices. So since the proportion is A, there's A squared. Things scale with T squared. here, this density scales with t. So this again synthetic scale with t squared. A is the density of sort of where I have this vertices with some feature which can connect into this sea of low degree vertices, this guy. And then in the end, I remove the isolated vertices. Or put differently, I have the limit is a multi-graphex, where now and this is still a function, this is still a constant, but this is now a natural number valued random variable, which is Poisson xy of the diagonal, and as usual, when you have these things, you get a different factor on the diagonal. And I sort of gave you the heuristic already. The heuristic, recall that this was Poisson. Then sampling distribution of this guy can be used to obtain these guys. Okay, and then asymptotically, if you put the two of together, you get what I showed you. And the other stuff are good vaguely as well. So I think I will not talk about uniqueness unless we have time. I should just skip it, or should I skip it?
I think you should do the 110-page proof. What do you think?
Well, so this is actually the uniqueness, and that uses the Semeredi lemma you want. Anyhow, I will not go into it. So we have this same picture Jennifer was drawing, and so we have sort of for dense graphs, we have these various convergent notions which are equivalent. We have rescaled convergence for sparse graphs, and we have sort of metric convergence, and I sort of talked a lot about the sampling convergence, where sort of Graphexes can be thought of as a completion of the set of sparse graphs in this notion of sampling convergence.